let's jump straight in then. So we'll talk a little bit about differential equations and how they work. So the idea of differential equations is that there's not going to be anything particularly new in this topic. The things that are going to be involved in this topic, the skills that you need for this topic will be already kind of present in your repertoire. So things like integration and differentiation are the things that you're going to use here. And in terms of the rules for them, you will have already learnt them in those calculus topics before. But the whole point is being able to apply those topics and apply that knowledge to doing a question which is more in an application sense. And that's what differential equations are. Cool. So essentially, when we talk about differential equations, it's kind of like talking about a polynomial, because what we're actually saying is we say differential equations of first degree, second degree, etc. And all that actually means is how many times we've derived that equation. So when it goes from y to dy dx to d squared y over dx squared, we go from, first degree to second degree derivatives, and that's kind of similar to first degree and second degree polynomials. So like the name suggests, the equations themselves, they'll have derivatives, and that's the whole idea of a derivative equation or a differential equation. So what we want to do is we want to do differentiation and integration normally, but then we're going to use those types of skills to actually solve their equations. Just like we have this whole repertoire of things that we do for polynomials, it's also building this repertoire of things that we use to deal with the differential equations. There's kind of two types of questions that they ask here. So they might ask you to just solve one of these antiderivative equations, and that, is a potential what they want you to do. Another type of question is they just ask you verify or show that. And often because these actual derivatives and things are actually quite complicated to do, and it's a bit difficult to antiderive something, or it's a bit difficult to derive something, often what they actually want you to do is just to prove that one of these things is a solution rather than coming it up with yourself, because it can be a bit tricky to do that. And if they want you to do that, it will normally be in the context of like an exam 1 question where you don't have a calculator around as well. Cool. Alright, so these differential equations are going to be classified by the order they're given in. So like we talked about before, if you have the first derivative, it's going to be a first order differential equation, and if you have the second derivative involved, which like this one, it's going to be a second order differential equation. So essentially pretty reasonable in terms of how they name it. So if you derive it once, it's first degree. If you derive it twice, it's second degree. If you derive it 3 times, it would be third degree. So you kind of get the drill from there. So that's kind of different. That's how differential equations are named and works. So in terms of actually doing it, so like I said, there's actually 2 different types of questions. There's verifying and then solving, right? So the verifying one normally kind of relates to more when you're talking about doing a differentiation on a complex equation that you're dealing with, whereas when we talk about solving, normally you're doing more anti-differentiation and kind of doing those types of things more. In terms of the steps, you'll get a differential equation and you will get a solution to it for verification, and your job is to essentially prove that solution works. So you have to show it all working out, because these questions will be show that questions. And essentially the key thing to do here is you want to pick one side, often the more complicated side, and just keep working on that side until you get your desired result, and kind of manipulate it so it fits with the other side, and then you can equate both sides. If you want to solve differential equations, you'll get a differential equation, and then you'll get conditions for that differential equation. Because remember, when we integrate, we essentially get a family of functions. We don't get an individual function. So we need an anchoring point to tell us exactly what function it is. So if we're looking at something like this, right, and we anti-diff to get a parabola, it could be here, 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 it could be here. So, it could be anywhere along that line. And so the whole point is we need at least one point in the line to tell us exactly where it's passing through. And these will mostly be first derivative ones, unless they are super duper straightforward and it just literally says d squared y over dx squared equals to something. In that case, still a second order differential equation, but not really, we don't really have to deal with the universe of the differential equations, more just integrating twice. Cool. Alright, so let's talk about this question here. So the number of mobile phones N owned by a certain community TS is going to be modeled by this equation. So 6 minus 3t negative 0.4t, where t is bigger than 0. So they want us to verify by substitution that log En 6 minus 0.4t or negative 0.4t satisfies this differential equation. Okay, so we look at this side. This side is evidently more complicated, so that's what we're going to work on. So we can essentially say that we're going to get that we want to say that the left hand side will equal to 1 on n dn on dt plus 0.4 log En minus 2.4. Right, cool. So that's what we can do here, and so this is our kind of log En equation in terms of what the equation actually is. And then now what we need to find is the extra thing that we need to find here is we need to find out what dn over dt is going to be equivalent to. So dn on dt is going to just be equivalent to us deriving this, or we can just derive both sides because we need to do a bit of implicit differentiation here. So if we do d of dt times log En, and that's equivalent to d on dt times 6 minus 3 e to the negative 0.4t. So on this side we'll just have dn dt times 1 on n, which is going to be equivalent to the 0 is going to disappear into nothingness, and we're going to get negative 3 times negative 0.4 times e to the negative 0.4t, which is just going to give us 1.2 e to the 0 into point negative 4t. Cool. Alright, so we've got that part. So essentially we've got the first part of the equation. Now what we can say is therefore our left hand side is just going to equal to this equation that we've just found here, which is 1.2 e to the negative 0.4t plus 0.4 times our log En, which is equivalent to 6 minus 0.3 e to the negative 0. Well, that kind of went off the page. Negative 0. Let's rewrite that part. Plus 3, minus 3 e to the negative 0.4t. So all that's going to work out to be is 1.4 e to the negative 0.4t plus 2.4 minus 1.2 e to the negative 0.4t. So therefore that's all going to be equivalent to, you can see how those two cancel out, is just that it's going to be, and then there's also a 2.4 at the end as well that we've got to add on. So plus 2.4 and plus 2.4, right? Or minus 2.4, sorry, not plus. Minus 2.4 and minus 2.4. So what we're going to get in the end is that we'll see that the minus 2.4 cancels out with the minus 2.4, and the 1.2 will cancel out with the 1.2, so that will just give us 0, which will give us right hand side as required. Cool, so we can kind of see how that all correlates together to give us the answer we need. Amazing. Right, so in order to do the separable differential first order equations, remember like to like. So essentially all you need to think about is, it's kind of a bit of dodgy maths to be really honest, but if you have something like dy dx equals to blah, essentially what you do is you separate the dx to this side and keep the dy onto this side, or you can flip the dy dx depending on whether you have y as the subject or whatever. But the key thing here is that you essentially separate them over. So you would theoretically think that, oh yeah, you would have blah dy equals to blah dx, but that's actually not mathematically correct. So just make sure when you're doing that step, just to add the integral sign at the front. And now suddenly that is mathematically correct. So you can just do something like that. So what you want to do is you want to rearrange, so x and dx is on one side and y and dy is on one side, and dy and dx are actually going to be numerators. So in differentiation, you have d over dx, which is you can see that the dx, or the factor that you're doing it by, is the denominator. In terms of integration, it's actually the numerator instead. Then what you're going to do is integrate both sides as per normal, because you have your function in terms of y and then you have your function in terms of x. And you can put the plus c on the x side. And then you can make y the subject to kind of rearrange your function and get your function down. Cool. Alright, let's clear that screen. So you can kind of see like this one. So if you have dy dx equals to fx gx, you can see that the fx goes onto the dx goes onto this side, and the gx comes to this side. So you'll get 1 on gx dy and fx dx. So then you can put the integral signs out the front of both of them, and that will give you your function that you want. I would say you don't need to put the plus c until you actually do the integration. So you would do the integration, you would get big fx plus c. So where big fx is your antiderivative. Okay, cool. Alright, so for example, something like this. So we have solved the following differential equation where dy dx equals to y over 1 plus x squared, where y0 equals to 1. So this is to solve that question. So we can see that we have the actual derivative, and then we also have an anchoring point to tell us exactly which in the family of functions is going to be. So then what we want to do here is get the dy and the dx on the same side. So we're going to move the y to one side. So we're going to get 1 on y dy is going to be equivalent to, and we're going to move the dx to the other side, 1 on 1 plus x squared dx. And then to make sure it's mathematically correct, we're going to just put the integrals in front of it. So 1 on y dy is just going to be log ey. And this one, if we kind of look at what type of thing this might be, this is going to remind us of our tan inverse function. So it's essentially just going to be tan inverse of x. And then we can put a plus c on the side. So therefore what we're going to get here is that modulus of y would equal e to the power of tan inverse x plus c. Right? And then because e of x, or e of a, is always going to be bigger than 0, therefore you would just get that y will equal to e tan inverse x plus c, because it will always be positive and y will never be in a negative kind of position. Cool. Alright, so then what you can do is you can sub in the 0 point. So you can sub in 0, 1. So we'll have that this is going to be 1 equals e to the power of tan inverse 0 plus c. So therefore we'll get that this is going to be e to the tan inverse 0, and if we think of what the inverse angle to 0 is, so when tan is equivalent to 0, that's just going to be when you get 0, right? Because you'll have sine equaling to 0 and cos equaling to 1 or whatever. And so that's when you're going to get 0 there. So essentially we'll just have 1 plus e to the power of 0 plus c. 1 equals e to the power of 0 plus c. So 1 will equal to e to the power of c, and c will therefore equal to log e1. Or alternatively, you can say what power would e need to be raised to reach 1, and we can conclude that c actually equals to 0 here. So therefore, in terms of the actual equation, so equation would be simply just y equals to e to the negative tan to the negative inverse x. Cool. So we can see we separated it out first, did the integration, right, sorted out the integration, and then rearranged to make everything nice and pretty. Okay, cool. So there's heaps and heaps of applications of differential equations. The main three things that you'll kind of see across your thing is growth and decay, concentration and mixing, and then the other one we'll be talking about like logistic equations and all that kind of stuff. So growth and decay, these often work on exponential models. Or when you're talking about cooling, which often is also an exponential model. And essentially what it is like if you were to set out a glass of tea on the side of your room, how long will it take for that glass of tea to cool to, I don't know, 30 degrees or something? So it's kind of that type of question. Concentration and mixing questions often people find a bit tricky, which is fair enough. The key thing to think about is what goes in and what comes out, and therefore what is overall change. Okay, cool. So if we're looking at something which is growth or decay, which is proportional to the population, right? So what we'll get is that, if y equals to the population, we'll get that dy dt will equal to ky. So therefore you'll get that y by itself will just be equal to a times e to the power of kt, right? And if k was bigger than 0, this means that this graph would grow. And if this t was smaller than 0, if the k was smaller than 0, that would mean that the graph would just shrink, right? In terms of the, like, whether it's going up or whether it's increasing, whether it's decreasing, right? So if the k is smaller than 0, that means that it's like 1 over something. So the thing, because it's 1 over e to the power of kt, or negative kt essentially, because that's going to be positive because this one was negative in the first place. And if you think about increasing the value at the bottom, you're going to be dividing by an increasing larger number. So therefore what you're going to actually get, instead of an increased value of y, you're going to get a decreased one, because you're dividing the number by a bigger and bigger number. Cool. And a is essentially just going to be our initial population or initial whatever, but often it's just given a random variable. As long as you know, like, it doesn't have to be a, but as long as you know that there is existing a variable, that's totally fine. Cool. So this alien population is increasing, and the rate of alien increase is proportional to the number of aliens present at any time t. So there is usually about 500 aliens, and they're growing at a rate of 100 per day. So what is going to be k? So what we can do here is essentially just set up that equation that we just did for the previous question, and essentially say that if you know that at t0, population p equal to 500, and it's growing at a rate of 100 per day. So what that means is that dp dt equals to 100, right? So you can kind of apply that into our function here, because we know that it's going to be proportional to the population, and it's 100. So the rate of increase is proportional to the number of aliens, so that will mean that dp dt will equal to k of p. So therefore k of p will equal to our 100, right? And our p was equivalent initially to 500. So, when it was equivalent to 0, it was equivalent to, when t was equivalent to 0, we can see that this was equivalent to 500. So essentially you're going to get that this is going to be 500 times k, which equals to 100. And because it's initially growing, that the initial rate for this growth of aliens, so growth of aliens at rate of k equals to 1/5 aliens per day. Cool. Awesome. Alright, so solve the differential equation to express p as a function. So what can we say? We can essentially use that equation from the previous one and put that in, so that you know that your p value is going to essentially be equivalent. So There's kind of like two ways to do it, right? You can either write it out exactly as you've done here, so you don't have to worry about it too much when you're going into detail about it. So what you can do is essentially you can say that your y, so you can say that your dy dt, dy or dp dt, just erase that. So your dp dt was going to be equivalent to 500 times k, which was going to be, or your p times your 500. So initially it was 500, and then so it would have been 1/5 of p. So therefore, if you're going to try and find out what that is going to be, you'll get that dt over dp is going to be equivalent to 5 over p. So therefore, your t value, so you want to find t at any time t, and you know that at t equals to 0, your population is going to equal to your 500. So what you're going to get here is that you can say that from t to 0, let's say 1 dt is going to be equivalent to 500, p to 500 5 over p dp. So you can kind of see how we move that to this side and move that to this side. So we'll have t minus 0 will be equivalent to 5 log EP p 500. So t will be equivalent to 5 log EP, and p is bigger than 0, so we can leave it as that, minus 5 log E 500, which will essentially just give us that this is going to be all divided by 5. So t over 5 will equal to log E p over 500. So e to the negative t over 5 will equal to p over 500. So therefore the final thing you'll get for p is p will be equal to 500 e to the negative 1/5 t. And if we check that with the equation that we just wrote out here, we can see that that's going to be the exact same, right? So because it's going to be growing at that rate of 100 per day, we can kind of see how that's going to be equivalent to the one that we just talked about before. And you can kind of see how when we subbed in that 500 gave us the same thing. So that's exactly what's going to be happening here in terms of our equation when we're kind of dividing across and moving that across. So I think this should just be positive 1/5. So you'll get that this is going to be increasing by essentially 1/5 every time. So as this increases, you're going to be increasing to infinity and beyond. So you can say that this would be that number of aliens. Cool. Alright, so another application which is quite similar to it is often they like to talk about like cooling or kind of warming up, and it's really based on, I've seen lots of questions where like they've had something in one environment, like a plant or something in one environment, and they get switched to another environment, and it asks you like how long does it take to heat up or something like that. Another type of question which is related to this is often they have something which is like they have a glass of coffee or they have a glass of tea, and they have this glass of coffee and tea and it's too hot to drink, so they set it on a counter and leave it according to the ambient temperature to allow it to cool. So this is using essentially Newton's law of cooling, and it's just based on the fact that if you put something which is warmer in a cooler environment, that heat will be lost to the environment, and eventually that the thing in the cup will cool down as well. So once again, we have this kind of basic equation which is negative T minus Ts, where Ts is going to be the ambient temperature, and then we can kind of get from there the equation of our whatever the thing is. So whatever teacup, whatever the thing is. Cool. So yeah, essentially it's just first principles. Unless you want to use first principles, you can do that, but otherwise you can just remember this formula and plug it all in. Just like for this one, we could have memorized the formula as well. Cool. Alright, so let's have a go at this one. So this is kind of the type of question you'll get. So it's normally a fluid of some sort. So Nick takes a bottle of milk from the refrigerator for baby Alex. To heat this bottle, Nick places it in a saucepan of continually boiling water. Let Y be the temperature of the milk at time t after B's bottle is placed in the boiling water. So a differential equation that models this increase in temperature of the milk while the bottle is still in the boiling water is dy over dt equals to a 100 minus y, where a is bigger than 0. So what is the milk temperature when the bottle is put into the boiling water? So when is the milk temperature? The milk temperature when the boiling water is put into the they're just stating the milk temperature which when put into the boiling water is going to be 5 degrees. Sure. So they want us to solve the differential equation that y equals to 95 degrees where t is the time. So they want you to show that it's equivalent to this. So rather than verify, they say show that. So you're going to start from scratch as much as possible. So when it's just put into the boiling water, it's going to be 5 degrees. So what that actually means to us is y0 is going to be 5. Okay. And we also know what dy dt is, which is a 100 minus y. So from that, we can get dt over dy is equal to 1 over a 100 minus y. So we're going to get 1 on t minus 0 will equal to 1 on a times your antiderivative of from what will it be, y to 5 because it's 5 degrees initially, and it's going to be 1 over 100 minus y dy. So we'll get that TA or AT will be equivalent to log e 100 minus y 5. So AT will be equal to log e 100 minus y minus log e 95, which if we kind of simplify that down, it'll be e to the AT will equal to 100 minus y over 95, because we know y cannot be bigger than 100. So if we kind of put that all in all, we'll get that this is going to be y is equivalent to 95. Let me just rewrite that first part. So it's just a bit of rearranging here. So it will be 100 minus 95 e to the AT as required. Cool. So you can kind of see how we introduced the variable, put them in, flipped it over until we got the variable that we wanted, and then from there we can kind of figure out how to rearrange it in terms of t, so it's y in terms of t. Alright, cool. So this is often the trickiest type of question. So it's about this concentration of mixing problems. So it's often this type of question where you have a mixture being poured in and that mixture is flowing out as well. So what happens is you need to figure out the inflow and the outflow amount. So they're mostly given in grams per minute, and the main thing is to consider the inflow and outflow as separate things. So you have your inflow part, which is the amount they tell you in terms of the concentration, and this is going to be your flow rate, right? And that's going to essentially give you your amount per grams per minute times your flow in. And then your outflow is going to essentially be however much salt was in the tank over the volume plus whatever the change in volume is times your flow as well out. And so what that overall is going to give you is you can just multiply that to get that flow amount. So it's really important to remember that you will normally get what this value is. So the main thing is actually in figuring out the concentration is figuring out how much volume is actually occurring at each time, rather than actually focusing on this component, because this component will be really hard to isolate by itself. Cool. So if they do give you initial like conditions, they don't count for this. Like you have to use later for the plus C. So you'll have to kind of put this in first and then use the plus C. Cool. So the main things is that there's two different types of situations. So the inflow can equal to the outflow, or the inflow is not going to equal to the outflow. And the main thing that's going to change here is this one, right? Because the inflow here won't be affected regardless of if, the inflow is 3 liters above the outflow or 5 liters above the outflow. All in all, if it was 3 liters or 5 liters to begin with, that's however much the outflow rate is going to be, or the outflow kind of concentration gradient is going to be. But in terms of the outflow, so in terms of the inflow, it won't matter, but in terms of the outflow, the main thing that's going to change is down here. So even though the amount of salt isn't going to change, the amount of volume is going to change, which means, so as the volume dilutes, it's going to dilute whatever the solid was in there before. So that means that the actual concentration will fall, which is going to affect the outflow rate. So the main two situations here, like we talked about, is when they're equal and when they're not equal. So if they're not equal, the easiest thing to do is essentially go V in minus V out, and that's what I like to do. So essentially I go that this is my V initial plus my V in minus our V out. So that way, if they both cancel out, peachy days. If they don't cancel out, you still don't forget about the effect of volume on your concentration. Okay, in terms of the steps, you want to draw the situation. You want to put an inflow, outflow track, and also the capacity of the tank. So something like that. And then you want to define your inflow and outflow formulas. And that just includes writing out how fast it's going in and also what's the concentration going in. Same thing here, how fast is it coming out and what's the concentration of the thing that's coming out. And then what you want to find is this amount is going in and this amount is coming out. So the main thing you want to find here is what is the difference in those two amounts. So how much salt is going in and how much salt is going out. And then what you want to do is you just want to solve for that equation and find whatever the Q value is in terms of T. Alright, so if we look at this one, cordial has 3 grams of sugar. Before selling it, it needs to be diluted to a solution of cordial that flows into a tank initially filled with 100 of liters of water which contains 20 grams of sugar. It enters the tank at 5 liters per unit and a uniform mix flows out at the same rate. Solve the differential equation for the amount of sugar in the mix. So we draw out our tank, we have something coming out of our tank, and we can have stuff going into our tank as well. So there's 100 liters initially, and there's 20 grams initially in the tank. So i.e., let's say sugar, so sugar 0 is going to equal to 20, right? Or 20 grams. Okay, so then we go in and then come out. So in terms of in, it's going at 5 liters per minute, and out is going 5 liters per minute. In terms of the concentration going in, we said that's going to be, so concentration is going to equal to 3 grams per liter. And in terms of what's coming out, if we name that S, so that was going to be, the concentration coming out would have just been S over your 100 liters plus your 5 minus your 5. So all in all, it's just going to be S over 500. So what we're going to get here is now we can combine them. So therefore ds dt is going to be equivalent to ds dt in minus ds dt out. So what you're going to get here is, in terms of your ds dt in, you're going to get that it's going to be 3 grams, right, times your 5 liters. So it's going to be 15 of these grams that go in per minute, right? So you have you have the 3 liters per gram, 3 grams per liter, you have your 3 grams per liter, and you have your rate of 5, so you have 15 kind of grams going in at one time. In terms of coming out, you're going to have your 5 times your S over 100, which is essentially going to just be C over 20 in terms of your amount that you're going to get in. So you're going to get ds dt is going to be equivalent to this. And they wanted us to solve it here, so that means that we need to do a bit more magic to allow this to work. So we got that this is going to be s over 5 to 20, and whereas this is just 15, right? So therefore we can say ds dt is going to be equal to 300 minus s over 20. So what we can say here is dt ds is going to be equivalent to 20 over 300 minus x ds. dt, sorry, not ds. Yes, ds, not d. So it's going to be equivalent to that. And then if you wanted to find t is just going to be equivalent to this ds. Cool. So then what we're going to get here is that we're going to get that this part at the bottom is going to chuck a negative out front, and we're going to have log n of our 300, so log negative 20 log n of our 300 minus our s. And that's going to be equal to our s value, right? Or our, no, sorry, it's going to be equivalent to our t value. So therefore what you're going to get here is that e to the power of negative 20 t is going to equal to 300 minus s. So you'll get that your s is going to be equivalent to 300 minus e to the negative 20t in terms of your amount of fluid and how much salt you have in the mixture. Cool. Alright. Let me know if there's any questions. So a visual representation of these is essentially called a slope field. So a slope field, like the name suggests, shows the slope of graphs. So it literally just dots out what the shape of the graph will be, and it helps you visually represent what a family of curves actually looks like. So you can kind of see how they're just all shifted up or down based on which one that you're looking at. And kind of note with these slope fields, it doesn't necessarily have to pass perfectly through each slope line. The main thing is that you need to make sure that you've matched your initial value well. So just make sure you're comfortable with at least doing a couple of these and see how you go with tracing them, because sometimes the tracing them can go a bit wonky because you follow a different path compared to what they've followed, and then you can kind of get a vastly different graph from there. Because if you might follow this one, you might see that it's a bit more curved, or if you look at this one, if you use like this here, right, so if you use like this point here, you can kind of see how that one passes through that point, but it might not pass through, let's say, like, we might go through that line instead, and then instead go more vertically. So there is a bit of leeway, but just make sure you get the point that they tell you exactly on the dot, and just try and trace as carefully as possible in terms of where it's going to be moving after that. And they will have a general shape in which you can follow, so just try and follow that shape. Alright, so this is calculator work, how it works in the calculator. So essentially what you do is you just like open your menu, and then there's a section where you can actually put in your differential equations directly in. The most important thing with this is that if you have your y being y1, it's important for you to type y1 in replacing your y component in your calculator. And similarly, if you're dealing with y2 or y3 or anything like that, just make sure to replace the letter that you've put in to make it clear to your calculator what you're actually talking about, because otherwise your calculator will refuse to do it. Cool. Alright, so in terms of slope fields, how we kind of identify them, so quick things to identify. So There's kind of a couple things that I think of in slope fields. So I first say, do I actually recognize the graph? Do I know what the graph is actually going to be? And is it like a polynomial, or is it a a circular function? So do I already have a shape that I've already identified that I know? So that's one thing, right? That's kind of the key thing. The second thing is now I'm going to start looking like along the axes. So I'm going to try and find when x equals to 0. So along here or along here. So if x equals to 0 here, I'm going to check whether that makes the graph undefined or makes the graph, completely flat along there. So that will indicate to me that x is either a factor or x is going to be underneath the graph, depending on whether it becomes undefined or if it becomes, just horizontal. Then what I'm also going to do is when I anchor it at a certain x point, I'm just going to look down the values like this. So I'm going to check at x equals to 1, for example, and I'm going to browse down the slope lines. And I'm going to check that all the slope lines are the same, right? So if I check that, if all the slope lines are the same, that means that the graph is solely going to depend on x, because if x is not changing, the slope is not changing. And I can do something similar for the y values as well. So if I move horizontally like this and the gradient doesn't change, that means that the dy dx would have solely depended on the y values, because the slopes aren't changing when we move horizontally. So that's a good way to check it. Another thing I've kind of already mentioned, but looking for asymptotes where they're undefined is really important. And then also you can kind of look diagonally. So you want to look for areas where your gradient is positive, gradient negative, and what happens in terms of the transition. So those are a couple of things that you can look for. And you can also look for like vertical lines, which indicate asymptotes, and horizontal lines, which might indicate stationary points. And you can also look for, if you know that it looks like a circle, you can also look for the center as well to give you a bit more information. Cool. So we want to look at the y-axis, x-axis for patterns. So like we talked about, 0 gradients, undefined, positive or negative. And then you want to look at the question. So we want to see if there's like vertical lines. So we want to look at the dy, dx's in terms of the options they give us. Because most of the time these questions are going to be multiple choice questions. I've seen like 1 or 2 off where they give you a slope field or they ask you to draw a slope field and then they might ask you to trace something. It's kind of a bit more rare compared to questions because it's a really easy VCA question. All they have to do is like generate a slope field on their calculators and then put it onto the exam and ask you what slope field it is. So it's a really good, easy question for them to ask, and they often like doing it. So being comfortable with kind of ruling out different derivatives or differential equations is really important. So look in the differential equation for any undefined lines, any 0 gradients, where it's positive or negative. And you can also draw the graph on the slope field. So remember, if you get stuck, you're in exam 2, you can always use your calculator as well. So you can graph out each of the different slopes. And my main tip for that is to make sure that the axis you set is the same as the axis that you see on the page, because that will make it a lot easier for you to compare between the two. And you can also set different amounts of like dashes in your graph as well, because that way you can also change how many dashes and the general trend of the graph you're going to see. Cool. So for a question like this, so the differential equation is best represented, the differential equation that best represents the above derivative field. So you'll note that you can kind of see this like X type pattern. So I actually think this is going to be like a north-south hyperbola type situation. So something like this in terms of the actual graph itself, right? You can kind of see how it vaguely has that type of shape. So that means that it's going to involve both the X and Y. So we can do our tests, right? So if we move along this axis right here, so if we kind of move along it's a bit hard to see, but if you kind of move along the vertical axis here, I can see that the lines are kind of going straight down like that. like that. So they're going straight down. You can kind of see how lines are going straight down. So what you can imagine here is that there is going to be some sort of asymptote when y equals to 0, right? So you know that you can see that there is some type of asymptote when y will equal to 0. So you know that you're ruling out essentially that you have a y at the bottom of your equation. You don't know what else you have at the bottom of your equation, but you know you have a y at the bottom of your equation. So that automatically rules out option A and option B. So then what you're going to do here is look for do the same thing except with the x coordinates. So you're going to look down the x, and you can kind of see that when x equals to 0, your gradient is going to equal to 0. So you know you have an x at the top at least. So you know that this so far is approximately what it looks like, right? So you know that there's an x and a y. So you can kind of rule out that option as well. So now we're just left with negative x over y and x over y. So those are our two options which are still available. The only difference between these two is that this is negative and this is positive. So what we want to look for here is we want to look for when x and y are both positive. So this is going to be in this quadrant right here, right? And we want to make sure that all of the gradients here within this quadrant are positive. And we can kind of see that is because they're all facing this way. And then we can do that double check, and we can check here as well. All the gradients here are positive as well. So if x is negative, y is negative, all the gradients are positive. And then we can check across here. So these are all negative, these are both positive, and that works out to be that it's just x over y. If it was this one instead, the orders would be reversed. So we would have positive in these two quadrants, because essentially you would have one being positive, one being negative, and then the extra negative would have made the gradients positive, and you would have negative in those quadrants. So you end up with option E here. And you can kind of see how these types of equations are just essentially ruling out ruling out the options you have until you can find what's going on. And that's why they do lots of multiple choice options with these, because these questions are actually quite hard to do unless you have a calculator, and unless you have a calculator, or unless it's a really simple differential equation to work with. Cool. Alright, so let's talk a little bit about Euler's method, or Euler's method. So it's the same Euler who made Euler's number, and essentially this is the Euler's method, right? So this is kind of similar to talking about when you're talking about the whole idea of getting this one, which was using the fundamental theorem, using the fundamental theory of calculus. So it was under that idea that essentially if you want what FB is, you can find what FB is, or just FB essentially. FB is by just going from B to A of f dash of x dx plus f of A. So it comes from that idea, because you can kind of see parallels, right? So if you want the next value along your line, I'll just clear this. So if you want your next value along your line, along this thing here, what the most important thing to do is, if you want that next value along the line, you want to know where you're coming from, what is the slope of the change, what is the length of the change, and that will give you the height of the change, right? So essentially this is like rise over run, right? And then you're timesing it by its run, so you'll get the rise. So therefore you add the rise to the previous y value to get the overall y value. So the whole thing is that you use this y value as your anchor point, and you're using this one as like the change in y. So this whole thing represents the change in y. So the easiest thing to do with this is, honestly, it's often not that common to come up as it's not an uncommon question, but it's not a very common question. So you can make you can code your calculator to do this for you if you can make up an algorithm for it. I would say if you have the time, sure, do it. This might be something worthwhile and it might help you get it into your brain as well. But I would say if you don't are a bit short on time, or if you have a lot of other stacks to revise for, it's probably not something I would bother with too much, because as long as you understand the method and what you're inputting, it often works out quite smoothly and your calculator does most of the calculations for you anyway. Cool. So essentially the steps here is you write your y1 plus your yn, and then you put, so that's your, like, the formula itself, and you want to count how many steps you want to do. So they might say something like you want to get from 1 to 2 and your step size is going to be 0.5. So you're going to go 1.5 and then 2. That's 2 steps, right? So you need to count how many steps you need first. And another thing is that can be really easy to mess up is this one is going to be the previous y and x values rather than the y and x values of the current thing, so of the current one. And the reason behind that is if you think of the whole idea of it, essentially if you know this value and you want this value, you want to draw a line from this value to kind of project where that value might be. And obviously it's going to be off because this is an estimation method, but the whole idea is you kind of draw a line to estimate where that line is going, and then you essentially times it by the run to get the rise out of it. So then what you can do is you can just do step by step. So often at most they normally do about 3 steps for actual, like, not calculus, but actual exam questions. They normally do about 3 or 4 steps, maybe 3. I would say mostly 3. For textbooks, they might get you to do like infinity and beyond, honestly, but it's just for practice and just so you can get comfortable with it. So in terms of something that you can code in that as well. So you can write dy dx, all of this put in, and you can write the Euler's thing. So you can kind of see how this works here because the gradient is rise over run, right? So if we wanted the gradient for this one, it would have been yn plus 1 minus yn over x plus 1 over xn, and this one is our run, which we've named our h value. So if you multiply out by that, you'll just get yn plus 1 minus yn. So that will give you, so if you kind of multiply it by that, you'll get yn plus 1 minus yn, so the yns will cancel out and you'll end up with yn plus 1. Same thing as, like I said before, with that whole concept of like the fb equals to b to a, why is it not working? B to a f of x dx plus f of a, because if you imagine what's going on with this one, essentially you're saying that fb will equal to, sorry, this should be f dash, so it's the gradient that you're looking at. So if you anti-derive that, that should just be the normal graph, right? So just be fx, ba plus fa. So what you're going to get here is that it's going to be fb minus fa plus fa. So you can kind of see how those two cancel out like that. And it will leave you with fb. Cool. So let's have a try of this now. So use the Euler's method to find an approximation to the solution dy dx equals to 2x for the interval 0 to 3, given that y0 equals to 0 and x0 equals to 0 using a step size of 1. So first we need to identify how many things we need to do. So we need to go from 0 to 1, 1 to 2, and then 2 to 3. So we can calculate 1, 2, 3 steps. We need to go 3 steps in total. Okay, so our equation is I'd like to name it y1 if I want to move on. So y1 equals to y0 plus h f x0, and you can, so the reason why they include here yn and xn is sometimes because, like we've seen with our differential equations, the derivatives don't just include x, they include y as well, so that's why they include both when they're talking about this. Most of the cases it actually will just be x by itself. Sometimes you'll have the y, but that just means that you need both values to be subbed in, which is fine, it doesn't actually make that much difference to what you're going to do. It just means that you have to sub in an extra value. Cool. So what we can get here is essentially we'll get that this is going to be y1 equal to y0, which is 0, plus h, which is 1, times f of 0. So f2x, which is just going to be 0, right? So we'll get that y1 will just equal to 0 as well. So y0 equals to 0, and y1 for us also equals to 0. Okay, cool. So we'll move on to y2 now. So y2 for us is going to be y1 plus h fx1. So our fx1 is our y1 is going to be 0 from our previous question, and our h is going to be 1, and our fx1 is now going to be essentially this value plus 1, right? Because we just worked out that that's the next value along. So again, it's going to be this one. So this is y0, y1, y2, y3. So y1, which is going to just be 1, so 2 times 1. So we're going to work that out to just be 2. Alright, so then we want to move on to our y. So our y2 is 2. So essentially that's what we're going to get here in terms of our value. So we move from y0, so this should be this is y1. So essentially when x equals to 1, you have y equaling to, so when x equals to 1, y equals to 0. When x equals to 2, y equals to 2. So therefore we'll move on to y3 now. So when y equals to 3, when x equals to 3, you're essentially going to get that this is going to be y2 plus h fx2. So that's going to be 2 plus 1 times x2, which is going to be 2 times 2 in terms of our value. So we're going to get this is 2 plus 4, which is going to equal to 6. So therefore, you'll get that the approximation to the solution for the interval of this to this is that you'll get that at x equals to 3, y will equal to 6, approximately. You can do a bit of an approx sign. And really important here, don't skip steps because it can get really easy to mess up. So because it's an approximation value, they'll ask you whether it's over an estimation, under estimation. So what you want to do is essentially just differentiate it and then just compare it. So like for this previous one here, right? So if we anti-differentiated this one here, so if we anti-differentiated this one here and to kind of find the value that we wanted, we would get that this is going to just be x squared, right? X squared and then essentially plus 0 overall, right? And then if we wanted to kind of find out what the actual value was, we would get that y equals x squared plus 0. So therefore, if we substitute that in, we'll get that y actually equals to 9 in reality. So we can see that that is an underestimation of the value of what y would be. Coolios. Alright. So let's move on to an example of doing that. So bacteria are spreading all over the petri dish modeled by this rate, where P is the proportion of the dish covered after T hours. Express 2 over P1 minus P in partial fraction form. So partial fractions to us, very helpful, great things for basically anything. So it's good to have all those partial fraction equations in your thing. So remember, if you have a linear factor, so just x minus a by itself, it just turns into a over x minus a. If you have a repeated factor, so x minus a squared, or let's say to the power of n, you're going to have a to the power of x minus a plus b to the power of x minus a squared until you have plus z over x minus a to the power of n. So you're going to do it that. And then the last one is going to be if you have ax squared plus bx plus c, where you have b squared minus 4ac is smaller than 0, so the discriminant is smaller than 0. And in that case, you're going to have bx plus c over ax squared plus bx plus c. So those are the kind of components, and you do a bit of a jigsaw thing. So for this, we just have two linear things, so we're going to express this as a over p plus b over 1 minus p. So what we can do here is essentially have a look at this, and we're going to say this is 2 over p 1 minus p. So if we times everything by p1 minus p, we're going to just get that this is 2a 1 minus p plus b p. And we can just do a bit of collecting like terms here. So we're going to get that 0 is going to essentially just equal to b minus a, and you'll get that a is going to just be equivalent to 2. So what you're going to get here is that if a is equivalent to 2, p is also just going to be equivalent to 2. So if we want to express this in partial fraction form, what we're going to get is that it's going to be 2 over p plus 2 over 1 minus p. And we can do a quick test, so we'll have 2 minus 2p and then plus 2p, and that is equivalent. So the 2p's cancel out, so that's equivalent. Cool. Alright, so hence show by integration that t minus c over 2 log e p minus p, where c is a constant of integration. Show that t minus c equals, yeah, cool. Alright, so we remember this is our equation that they wanted us to do. So our dp over our dt was equivalent to p over 2 1 minus p. So if we kind of undo this, we'll say that dt over dp is equivalent to 2 over p 1 minus p, which coincidentally is our p over 2 plus 2 over 1 minus p from before. So therefore, if we kind of do it from here to here, we can say from t to, they just did the constant of integration, so we can use that form that they wanted us in rather than doing the terminal one. So what we can do here is we can just say t is going to be equivalent to antiderivative of 2 over p plus 2 over 1 minus p dp, which is going to be equivalent just to 2 log e p minus 2 log e 1 minus p, because of the p being negative here, and then plus c at the end. So that's equivalent to t, and then we want to kind of make sure it's in that form that they wanted it in. So we can go t minus c over 2 to divide that out is going to be equal to log e p minus log e 1 minus p, which means that t minus c over 2 is going to be equivalent to log e p over 1 minus p. And then as p, and they've told us that p is equivalent to something, so as p is bigger than 0, smaller than 1, therefore you'll get that p is going to be bigger than 0, and 1 minus p is also going to be bigger than 0. So therefore you'll get that this is going to be t minus c over 2 will equal to log e p over 1 minus p, as they require. Cool. Alright, so if half of this petri dish is covered by bacteria at t equals to 0, express p in terms of t. So essentially what they want here is they want us to say that in terms of this equation, half of the petri dish was actually going to be covered by that point. And remember, our p value is going to just be essentially telling us that the proportion of the dish that was covered after t hours. So essentially what they're saying is that p equals to a half at t equals to 0. So if we write that out in terms of our equation, which was t minus c over 2 equals to log e p over 1 minus p, I think. Yep. So then we can substitute that in. So we'll have that 0 minus 2 over c will equal to log e a half over a half, right? Because a half and then 1 minus a half is a half anyway. So we'll just get that negative c over 2 will equal to log e1. And log e1, remember that's just equivalent to 0 because essentially e to the power of 0 equals to 1. So we'll get that c will equal to 0. So therefore all you're going to get here is t over 2 will equal to log e p over 1 minus p. So you'll get that e to the power of t over 2 will equal to p over 1 minus p. So you'll get that e to the power of t over 2 minus your e to the power of t over 2 times by your p is going to be equivalent to p. And then we can take all the p's to one side. So we'll have that p and put that onto the other side. So we'll have 1 plus e to the power of t over 2 will equal to e to the power of t over 2. So we'll get that p will just be equal to e to the power of t over 2 over 1 plus e to the power of t over 2 as our equation. Alright, so then after 1 hour, a toxin is added to the petri dish which harms the bacteria and reduces the rate of growth. So the differential equation that models the rate of growth is now going to be different, which is now going to be this instead. So they want us to find the limiting value of p, which is the maximum possible proportion of the petri dish that is covered by the bacteria, and give our answer to 3 decimal places. So in order for our max value covered by bacteria, essentially we need to solve for dp dt is equivalent to 0, right? Because this will show where our stationary points will occur. So what we're going to say is 0 is going to equal to p over 2, 1 minus p minus root p over 20. And what we can do once we do that is, because this is correct to 3 decimal places, they're probably suggesting for us to solve that onto our calculators. So that's exactly what we can do. Alternatively, another thing you could do here is you could move the root p over 20 onto the other side and do a bit of squaring, and by that you'll get like a polynomial which you can work out as well. But for our purposes we can just do this instead. So we'll have p over 2, 1 minus p minus root p over 20 is equivalent to 0 for p. So it gives us a couple of different values. So it tells us p could equal to 0, p could equal to 0.01, or p could equal to 0.89, right? And the key thing here is that we want to make sure that these are all possible. So you can kind of see how the maximum is already given by, you can like already look and see that that is the maximum that's going to be possible. But the main thing is that we want to make sure that this is going to be possible for our t value as well. So what you could do is evaluate this for our t value to make sure it was possible in the first place. So i.e. t is going to be bigger than your 0 or your 1. So what you can do here is essentially, if you go back to the previous equation here, you just want to substitute into this to make sure that it works out for that. So you can go e to the power of 1/2 over 1 plus the power of 1/2. So you can see that that's going to be 0.66 something, right? So you know that it's going to surpass that level in terms of when that's going to be. So therefore, the max coverage is going to be 0.894. And you can just say max proportion coverage, or however you want to say it. Yeah, and there's not really a unit for this one, I guess. So you can just leave it as is. Cool. Alright. So a little bit more to this question. So the total time t hours measured from time equals to 0 needed for the bacteria to cover 80% of the petri dish is given by this equation. So you can kind of see how that exactly is our fundamental kind of theorem of calculus type thing. So where Q, R, and S all belong to R. Find the values of Q, R, S, and giving the value of Q correct to 2 decimal places. Cool. So what we can see here is that it needs to cover 80% of the petri dish. So right away we need that P to equal to 0.8. We also want here that we want these 2 values to tell us when this is going to occur, right? So we want to know when exactly those 2 values are going to occur. And this thing is actually going to come from our own values of what's going to be going on. So this, in terms of like a time is going to require for this to happen, right? We want to know how much time it's going to be from t equals to 0. So what that means is that if we think of what's going on in terms of the timeline, in terms of how long it will actually take, right? It will take the time, so it will take the time of t, so however many seconds it is. So because this equation only works from t equals to 1, essentially what you need to do here is kind of measure it from t equals to 1. So what you're going to do is essentially you're going to say that this, if we were to set up this equation, it would essentially be that you have your, just rub that bit out actually, you have your dp dt from before, you have your dp dt from before, which was this one here, right? And you're going to say that's equivalent to your p over 2, 1 minus p, root p over 20, and that's how it's going to be converted into this one. So eventually you'll end up with t to 1, because you're essentially going to add that 1 second on at the end to find out when it's going to reach that point. T to 1 dt is going to be equivalent to saying that this is, so yeah, you flipped it over, so you flipped it over, and then it's going to be equivalent to saying that you want 80% to be covered, and you want to know how much is covered at t equals to 1, right? So essentially t equals to 1, you want to know how much was covered at that point, which we coincidentally actually found for the previous one. And we know that's going to be 0.62245 ... So therefore this one here is going to be 0.26, so this is 0.8, 0.26, and this is 2 decimal places, so 0.62, and then we're going to have 1 over p over 2, 1 minus p minus root p over 20 dp, right? And then if we were to undo this one, and we can rub out that side so it's a bit cleaner, essentially it would just be t minus 1 in terms of the time, so t minus 1, and what we're going to get here is that, therefore we'll add the 1 to the other side, so we'll get that q, which is this one here, will be 0.62, our r, which is up there, is going to be 0.8, and our s is just going to be 1. Cool. Alright, last part to this question. So given p equals to 0.75 when t equals to 3, use Euler's method with the step size of 0.5 to estimate the value of p when t equals to 3.5. So you can see that it goes from 3 to 3.5. So you can see that it's only going to be one step. Alright, and it's given 3 marks for that, which is quite kind, I guess. So p0 is going to equal to 0.75. I guess we can go with p3 actually instead to make it a bit easier to understand. So let's go with p3. So if we want p3.5, we're going to get, that's going to be p3 plus h, which is going to be our 0.5 here, times our, what was that function? So our dp dt at t equals to 3 and p3 equals to 0.75. So if we look at the equation we're going to use this one because t is bigger than 1 here. So that's the equation we're going to use. So if we put that in to our equation here, so p3 is 0.75 plus 0.5 of, and our equation dp dt was something like p over 2, 1 minus p minus root p over 20, I think. Let's just do a quick check. Yep, looks good. So therefore what we can do here is we can substitute that in, and so the t doesn't actually matter in here, so we can just leave that. So we'll have 0.75 over 2, 1 minus 0.75 minus 0.75 rooted over 20. And then we can put that all into our calculator, or you can find it by hand, up to you. But we can put this into our calculator, so 0.75 over 2 times 1 minus 0.75 minus your 0.75 rooted over your 20, which is going to be 0.05 something, and then you can times that by 0.5 to get you 0.025, and then you can plus that onto your 0.75 value, which all in all is going to give you equal to 0.775 dot dot dot. So therefore P at T equals to 3.5 is going to be equivalent to 0.775. And there's not really a unit once again. Cool. Alright. So kind of summarizing differential equations, essentially there's a couple of different things that you can know. So the fundamental theorem of calculus, we've practiced that quite a bit with kind of separating the values on both sides. The separation of values, so essentially that dodgy mass where you move one thing to one side and the other thing to the other side and kind of separate it out and do the anti-differentiation of both sides at once. And make sure to put the integrals in as soon as you do the separation. There's growth and decay, which works with the differential equation as well, and with cooling and with the growth or decay of bacteria. And we also talked about the different problems, so the cooling problem, and then also the mixing problem, which is to do with the inflow-outflow type problems, and just make sure you know whether the volume is changing or it's staying constant. And the last couple bits was looking at slope fields, so make sure to look for patterns, make sure to look for when y equals 0, x equals 0, make sure to look when things are positive, things are negative. And then we also talked about Euler's method, which really is important to organize your working well in terms of what you're doing. Cool. Alright, so